I'd like you all to imagine that each one of you is walking the back stairway back in the corner here of my hallway. It's the one that goes up halfway, and then you go across to the little landing, and you go up halfway again. I'd like you to imagine doing that. Just imagine walking it. And now I'd like you to imagine sprinting it as fast as you can, using the railing to yank yourself up, trying to do the stairs 2 or 3 at a time. In which of those two situations, walking the stairway or sprinting the stairway, do you do more work? Ryan, why are you shaking your head? Okay, how much work are you doing if you wanted to calculate it? What work are you doing if you're lifting something against gravity? I heard someone whisper it quietly. There was 3 letters. I heard someone. Yeah, MGH. Okay, so it's the same amount of work. In which one would you be more tired? Why sprinting? So tiredness is not work in English in terms of your body. What causes tiredness is how fast you do the work, the rate at which you do the work. And Clarissa, the rate at which you do work is called power. If you're getting tired, it's not because you're doing a lot of work. It's because you're doing a lot of work quickly. It's because your body is generating a lot of power. So I wrote down here, the word power is used in a variety of ways in everyday language. Let me pause the video. Power, although it's used in everyday language, has a specific meaning in physics. If you want the physics definition, power is the rate at which work is done, or the rate at which energy is transformed from one type of energy to another type of energy. It's how fast that transformation is occurring. It is a scalar. Anytime we talk about the rate that something is done, you're dividing by time. So power is defined as work over time. It must be a scalar because work is a scalar, time is a scalar divided by a scalar. Where would you get a direction from anyway? So power is also a scalar. What would the units be? Well, technically the units for power are a joule per second, but the concept of power is so important, we've given this its own special name. Power is measured in what?
What?
In watts. Symbol, capital W. And this is where you have to be a bit careful because the equation for power has a W in it, that's work, and the units for power are a just W. Just don't get them mixed up. I've gone on my rant about how we're running out of letters in the English language. We should have had more, but it is what it is. So if you're expending energy, it's not how much work you do that makes you feel tired, it's how fast you do the work, or how much power you generate. What really leads to tiredness is power. It's the difference between walking slowly up a hill and sprinting up that hill. You do the same amount of work, one of them you're going to be way more tired. You burn more energy faster. In fact, really, this is how stairs and ramps work. If we wanted to do things the most efficient possible, we would have no stairs in our school. We would use ladders, because that's the shortest possible distance to get to the next floor, and work is force times distance. Of course, by lengthening the distance, not only can we bring the ramp principle in and lower the force required to raise that, to do the same amount of work, we're also increasing the time it takes, and so you're less fatigued. We can make stairways shallower and shallower if we really, really wanted to. The back stairway back there in the back field is a good example of an awkwardly shallow stairway that works great for senior citizens, but you guys probably find it awkward because it's just not made for your bodies are still able to sprint or move fairly quickly. Doesn't work well for us. It's a compromise. So stairs and ramps, you expend the same amount of energy. In fact, MGH, if you want me to be fussy. But you take more time, so you feel less fatigue. Example 1. A 60-kilogram girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. The stairs back behind here are around 3.5 meters high, so this is really close to that stairwell. What's her power output in watts? Matt, what's our equation for power? Yep, work over time. Now, when you go upstairs, Ryan, what did you say was the amount of work that you were doing? How did we calculate it? Yeah, and again, let's be fussy. What we're really saying is the force that you're pushing up with is the same as gravity. We're almost always assuming you're going at a constant speed, minimum amount of work. But yeah, it's going to be mgh over time. So it's going to be 60 times 9.8 times 3.32 all over 2.6. What do you get? 751 units. Power is measured in watt. Watts. Watts are the SI, the metric system unit of power. The imperial unit of power is the horsepower. 1 horsepower is about 750 watts. So what's this girl's output in horsepower? Almost exactly 1 horsepower. But I cooked the numbers a little bit to get that to be the case. But all of you could do that staircase behind me in 2.6 seconds. You wouldn't be walking it. You wouldn't be sprinting it. You'd be the quick step that you do if you know there's like 30 seconds left and you want to hustle to class, but you're not going full sprint. And you could probably do that several stairs in a row. All of you are capable of putting out 1 horsepower, 750 watts, for a reasonable amount of time. If you're in better shape, you could probably put it out for 30 or 40 minutes straight. If you're not in great shape, all of you could still at least do it once. The watt is named after James Watt. If you ask me who may be the most overrated person to have an important unit named after them is, my answer is always James Watt, because the watt is a hugely important unit. It's also going to show up again in physics. And he really, in my understanding, didn't do much for science. Some people will say, well, didn't he invent the steam engine? No, he improved the steam engine, but what he really was a good marketer. He had these improved steam engines. He was British, so he was in Britain, and he was going around to farmers trying to convince them to buy a steam engine. And of course, the farmer would say, what am I going to use this for? James Watt invented a unit called the horsepower. So he would say to the farmer, oh, this engine has 4 horsepower. The farmer instantly thinks, this motor will do the work of 4 horses. By the way, it does not. The horsepower has very little to do with horses at all. It's a made-up unit. Okay? But it was a great sales pitch. In fact, it was such a good sales pitch of a unit that we still use it today to describe car motors. And we don't live in a horse culture at all. None of you know how much work an average horse can do in 1 second. So the Watt, James Watt, overrated. I wish they would have named it after somebody else, but okay. Example 2. You don't need to memorize that 1 horsepower is 750 watts. If I do ever ask you to do the conversion, I'll give you the conversion factor in the question, or it will appear right above the question, like in example 2. Example 2 says, how long would it take a 5 horsepower motor to lift a 500 kilogram safe up to a window 30 meters above the ground? Okay. William, what's this question asked me to find? Time. There's lots of ways to find time, but the fact that I also noticed they gave me power, I think I'm going to write the equation for power, because I know power has time in it. But William, where is that T? On the... Blech! Oh, wait. Multiply it to the top on the other side, right? Oh, and then how would I move the P over? Yep. So time is going to be work over power. Ooh, why can't I use that 5?
Because it's horsepower.
Okay, so I'm going to, in the margin here, say power equals 5 horsepower. Remember unit conversion that we did last year? I want horsepower to cancel. I want watts to stick around. 750 watts is 1 horsepower. I can do that in my head. 2,800 plus 3,750? No. Yes? Yeah. 3,750? Yeah. So on the bottom, I'm going to have 3,750. On the top, since we're lifting, Ryan has pointed out that's MGH. So it's going to be 500 times 9.8 times 30 divided by 3,750. Going from memory, I think this actually works out like to a non-yucky decimal, something point something. Or am I remembering correctly or not? What'd you get? 39.2 seconds. What if you want... Sorry? Oh, power, not time. Thank you. What if you want this done faster? You would have to get a bigger motor. You could do it slower, just don't run the motor at full output, but you can't do it faster. Now, I got to be honest, this is kind of a trivial question. Maggie, meh, big deal. But replace safe with cargo ship at the Port of Vancouver. Replace 5 horsepower with whatever power the cranes at the Port of Vancouver use, and you can pretty accurately calculate how long it's going to take you to unload a cargo ship. And I'm sure they use software to do all that, and that way you know when to bring in the next ship. You'd have to work in a bit more because as you're reaching further and further down the cargo ship, the H would be changing, but you could calculate that in pretty easily. And then the cranes move sideways and lower the object, the shipping containers, onto something else, but you could calculate that pretty accurately. I'm sure they start with this, and they can run those numbers pretty accurately, probably to within the minute or even closer, how long it's going to take them to unload each ship, and you can get the ships coming in and out. So some nice applications there. Power is what over what, Matt? Work over? And work, Matt, is what times what? Force times? Anyone? Distance. I thought you were the one that I was going to on that. Maybe I'm misremembering. So force times distance. So you can think of power as force times... No, it was Cole. It was Cole, wasn't it? Cole was my force times distance person. Okay. You can think of power as force times distance over time. Can you all do me a favor? Can you circle this distance over time right there? Yes. Circle it. What are the units for distance? Meters. What are the units for time? So what I've just circled is meters per second. Ooh, what do I measure in meters per second?
Speed.
Yes, speed, not velocity, because we're in scalarville in this unit. Another way to calculate power is a constant force times a constant speed. Did I give you that one on your formula sheet? In previous years, I haven't. In previous years, I made students derive that. But did I give you power equal? I did? Wow. I won an award and I got mellow. I used to be way meaner. I think I'll take that off next year. Okay. And by the way, I should be careful. I need to fix this. It's not average velocity, it's average speed. Constant speed or average speed, I'll give you a constant speed. I'm not going to give you a changing speed and say, find the average. So that's a little bit about power. Remember that. We're also going to talk about efficiency. Efficiency means, in English, we have an expression, how much bang we get for the buck. Efficiency is how much useful power we get out as a ratio divided by how much power we put in, or how much useful work we get out divided by how much work we put in, or how much useful energy we get out divided by how much energy we put in. It's usually expressed as a percentage. The Greek letter eta, and eta looks like this. It's a lowercase n with kind of a droopy tail. It is where our lowercase n came from, is the symbol for efficiency. I didn't know that that was the symbol for efficiency until only a few years ago. So if you look at my answer keys online, often you'll see my symbol for efficiency was EFF period, efficiency. So just letting you know. How do we calculate efficiency? Well, it's the power we get out divided by the power we put in. Or the work we get out divided by the work we put in. Or the energy we get out divided by the energy we put in. And then we typically multiply by 100 to turn it into a percent, because this will be a decimal. I think I gave you that on your formula sheet. I never actually remember that. Here's what I remember. make sure you're dividing watts by watts or joules by joules. Okay, don't be dividing joules by watts. I know that the law of conservation of energy says that things can't be more than 100% efficient because that would be free energy. So here's what I memorized the efficiency formula as. It's always going to be the smaller number divided by the bigger number. Can't be more than 100% efficient. Now, the reason I'm saying that, by the way, is the power in, or the work in, or the energy in, when we get to electricity, we're going to be doing, there's a question in your future, sometime in May, where I'm going to ask you to calculate the efficiency of a light bulb. And the problem is, you plug in to an outlet in English. And so the source of the energy in is coming from an outlet. I've lost track of how many students put the power in the out spot because, well, isn't that the word outlet? And they try and tell me that the light bulb is 150% efficient. I will mock you mercilessly if you make that mistake and commit to that answer as your final answer, because that violates the law of conservation of energy. Now, Oscar, if you do actually invent something that's more than 100% efficient, the fancy word we say is more than unity, hey, you'll get a Nobel Prize in a couple of years. They'll name a unit after you, and if you play your cards right, in about 5 or 6 years, you'll be able to buy and sell Bill Gates. You'll be the richest person on the planet. If you give us free energy, right now, even with our current level of technology, we can probably engineer our way out of most of the world's crises if you just give us free, clean energy, unlimited energy. Oh, we got a food shortage? Oh, okay. You know what? If you give me free energy, I can power sun lamps at night so I can double the plant production because I can have them grow at night as well as during the day. Got it. No problem. Oh, we have a water shortage? You give me free energy, I can start desalinizing the ocean, no problem. We're not going to run out of the ocean in a long time. I can get us fresh water, no problem. There's very few issues that we couldn't engineer our way out of with something that was more than 100% efficient, for what it's worth. So I wrote here, efficiency is always less than 100% unless you plan on winning a Nobel Prize. It's not going to be more than 100%. Mr. Dueck, what, Nick? Can efficiency be exactly 100%? No. Yes. No. It really depends, and now we're going to get into some weird phenomena. Nick, there's something called superconductors, which we discovered, I think it was in the 1950s. Superconductors are conductors that have no resistance whatsoever, zero resistance. So normally, when you're sending electricity, electrons, through a wire, they're bumping into other molecules, and they're generating some heat, and that heat's coming from their energy. We're losing energy to heat and other sources. A superconductor, when you send electrons through it, they don't lose any energy whatsoever. So you could make an argument that a superconductor is 100% efficient, except if you zoom out, the only way you can get a superconductor to become a superconductor is to cool it. Sometimes you have to cool them with liquid helium. We have some that you can cool with liquid nitrogen, but that takes massive amounts of energy. You're not coming out ahead there. You're still losing a lot of energy. So the reason I said both yes and no, it depends on how far you zoom out. A typical light bulb transforms energy at a rate of 60 watts. Most, if we're talking about an incandescent bulb, the ones that you all grew up with, most of the electrical energy is actually transformed into heat instead of light. So about 57 watts, remember a watt is a joule per second, so about 57 joules per second of heat is generated, and only about 3 joules per second of light is generated by an incandescent bulb, but incandescent bulb is only about 5% efficient. Okay. Some well-meaning politicians a few years ago who didn't have a good background in science saw that, and they thought, we're going to ban incandescent bulbs because that's wasted energy, they said. Well, it's not wasted energy. If that bulb is inside your house, your parents' heating bill is lower by exactly that 57 joules per second, that 57 watts. That's not wasted energy. It's heating up your house in the winter. The politicians initially wanted to replace them with those spiral CFC bulbs. Do you remember those ones? Okay, those are really a big issue. If you have any of those, please, once they burn out, do not throw them in the trash. You have to dispose of them properly. Take them to the recycling place. They have mercury in them. If you throw them in the trash and they break, and they will because they're fragile, and they end up in a landfill, and they will if you throw them in the trash, that mercury is going to leach into the groundwater, leach into the ocean, and we do not have the technology to remove mercury from the oceans. We don't know how to do that yet. So you have to dispose of them properly. Also, those CFC bulbs don't work well outdoors in moisture. And so you might say, because the incandescent bulbs, well, that heat is wasted outdoors. It is wasted outdoors, but the CFC bulbs don't work very well that way. You might say, Owen, but in the summertime, we don't want to heat up our houses, so then the light bulbs are very inefficient. True. What country do we live in, Owen? In the summertime, do we have long days or short days living in the northern hemisphere where we do? Do we use bulbs more in the summertime or less? When it gets warmer, do we use light bulbs more or less? Far less. This was really a poorly thought out. It was a well-meaning politicians' move, but they really didn't think it out well when they were wanting to push those CFC bulbs. Now, LED bulbs, those are a much better alternative. How many of you have started replacing LED bulbs in your houses? Have you noticed it? Yeah. So I did all mine a few years ago, and that's the way to go. They've become much, much cheaper. They'll last a long time. They use less power. So LEDs. A kettle might transform energy into heat at a rate of 1,500 watts, 1,500 joules every second. Basically, if it's an appliance, the more heat it's moving around, the higher its wattage. The appliance in your house that has the highest wattage is almost certainly your dryer, your clothes dryer. In fact, if you pull it off of the wall, you'll notice it has a special bizarre outlet designed just for the dryer, and your stove also has one as well. It's sending a higher wattage, a higher current, and a higher voltage because it's moving so much heat around. In Europe and in North America, for an appliance, it's mandated that the wattage is printed on it somewhere. So if you ever want to figure out how many watts an appliance is using, usually it's printed on the bottom or it's printed on the back. Example 3. A 250 kilogram mass is lifted at a constant speed of 2 meters per second for a distance of 12.5 meters. Maggie, what's A want me to find? Okay. My first thought is work equals force times distance. Did they give me a distance in this question? Okay, I think I'm going to go with that. Otherwise, I'd go for the work energy theorem, which is change in potential plus change in kinetic. What's the work when we're lifting? Sorry, what's the force when we're lifting? I'd like you to imagine the free body diagram in your head right now. What are the forces acting on this object? Get the obvious one. Yep. Does it say constant speed in this question? So what's my acceleration as a number exactly? So the forces are, I'm looking for it begins letter B. Balanced, which means the lifting force, because really this is going to be the force of the lift times distance. I'm going to argue that the lifting force must be exactly the same size as mg. So I can replace this with mg times d. It's going to be 250 times 9.8 times 12.5, which is what? What'd you get, Maggie? It's going to be something in the 30,000s, I think. But I can't get much more than that. What'd you get, Maggie? 30. And I'm going to keep the extra couple of sig figs because we're probably going to use this, okay? B. Maggie, what's B want me to find? Power. My first thought, don't write this down, my first thought would be work over time, and work would be mgh. Do you see a time in this question anywhere? Ooh. Well, we had another definition of power. Force times speed. Did they give me a constant speed? Oh, okay. I know where we're going with this. Which force, by the way? The force of the lift. How big is the force of the lift? In my free body diagram, I don't know the force of the lift. Oh, but look, same size as mg. So this is going to be mgv. It's going to be 250 times 9.8. Oh, I can do this in my head. Times 2. 500 times 9.8. Double check me. 4,900, I think. Maggie, power is measured in watt? Yep. So we're using 4,900 joules every second. C. If the motor is using 10,000 kilowatts, how many watts would 10,000, sorry, I said 10,000 kilowatts. I gave away the punchline, didn't I? How many watts would 10 kilowatts be? 10,000. Sorry, I did the conversion in my head. Find its efficiency. Well, efficiency is going to be the smaller number over the bigger number. And you know what? I'm not going to use the 30,625 joules. And the way I know that, Maggie, is they gave me 10,000 watts as the, you know what? That is the power in. And the power out is 4,900 watts. Okay, I think it's going to be 4,900 watts divided by 10,000 watts, and then times 100 to make it a percent. And I can do this one in my head as well. It's got to be 49%, I'm pretty sure. Yes? Double check me, but I think so. Yeah. So this motor, Maggie, is 49% efficient. By the way, for what it's worth, that tells me this is probably an internal combustion engine, a gas motor. Gas motors are not very efficient at all. Where does a lot of the energy in a gas motor go to? Heat. You run your motor for a few minutes, pop the hood, you can't put your hand on the motor. Also sound, you can hear a gas motor from a long ways away. Electric motors are way more efficient. They don't give off much heat. And one of the neat things about electric motors, in a gas motor, if I floor it, if I step on the gas, that's when it's at its least efficient because it's throwing off the most heat. In an electric motor, if you floor it, if you step on the, whatever the equivalent of the gas is, that's when they're at their most efficient. That's when they give off the least amount of heat. So electric motors are kind of nice that way. You want to cool off an electric motor, rev it full. If you're ever using a power drill, for example, and you feel that the drill is starting to overheat, it's getting warm to your hand, it's because you've been running it slowly under load. Take it off of the load and just hold the trigger down for a few minutes in midair, and you can put your hand against it and you'll physically feel it cool off very, very rapidly because it's at its most efficient when you're running it at its maximum. Why is that, Mr. Dueck? Hopefully we'll talk about that in late May, early June. Example 4. Example 4. Oscar, what's example 4 want me to find? Okay. Power is going to be work over time. Did they give me a time in this question anywhere? Say no. No. Did they give me a speed? A constant speed? Speed times force. Force times speed. Which force? That's a little trickier. Is there a coefficient of friction in this question? A mu? You know what this might be a good job for? I think I'm going to do a free body diagram. I'm just going to do it over here. What are the forces acting on this? Get the obvious one. Yep. What else? It must be a normal force. And then I guess we're pushing with an applied force. And in fact, that's the force that I would like to figure out how much power is using. Okay. What else? How big is friction going to be? Sorry? I absolutely disagree with you. Why can't it possibly be smaller than F applied? So if it's a constant speed, the forces must be, I'm looking for a word that begins with the letter B, balanced, which means That. So I would say to you, I don't know F applied. Oh, but look, 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 look. I know another force the same size as F applied. Which one? And friction is going to be mu times the normal force. So it's going to be mu. I don't know the normal force. Oh, but look, 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 look. I know another force the same size as the normal force. I'm going to get mu mg d. The power is going to be 0.25. I might be able to do this in my head. 100. 9 point. Sure, I can. 100 times. Sorry? D is V. Why did I put a D there, Mr. Dueck? I put the right number in. I just wrote the wrong thing. Oh, because we had a D last time, I think. Dumb brain. 500, so got to subtract. Is it 490? Watts. Okay. I like example 5 in that don't put a star next to it. It's a lawnmower question. How do I know example 5 is a lawnmower question? Okay, it says the word lawnmower, but even if it hadn't, there's an angle. So I could do this. I would do a good free body diagram. I would have an Fx and an Fy. The normal force would not be mg. I could do this, and it is nerd cool, but I've told you on your work energy test, I'm not going to put a bunch of angles. So as much as I'd like to do it. And example 6, where it says nasty, also a lawnmower question. And again, we could do it all, and it's kind of cool, but I'm going to pass on it. It's Christmas. I do like example 8, though. I'm not saying I like example 8, I like example 8, I like example 8. I'm saying I like example 8 because I can teach you something about exercise machines. If you've ever used an exercise machine, most of the modern ones, when you're done your workout, they'll tell you how many calories of energy you burned. Calories are another way to measure energy. And it's nonsense. It's garbage, whatever they're telling you. And I'm going to explain to you why it is here. On a stair climber at the gym, a 75-kilogram person lifts their center of mass up 22 centimeters with each step. If they take 360 steps in 6 minutes and their muscles are 18% efficient, then find. Nick, what's A want me to find? Oh, yeah, the rate at which the person does work, the rate at which work is done is the definition of power. So I'm going to go power. Am I going to go work over time? Did they give me a time? Yeah, see, Oscar, that's how you do it. You look really quickly for minutes or seconds, or then you can figure out there's a time. Okay, so I'm going to go with that. How much work? Well, lifting. So again, it's going to be Ryan's MGH. All right, Nick, what's the mass? G, 9.8. What's the height? Don't say 22. Are you going to be the first one to catch it? Let's find out. And don't say 0.22. What are you going to say? What are you doing? Tell us what you're doing. Used a calculator to divide by 100? No. And it's not 0.22, by the way. What's the height? What? 360 times that. Oh, Nick, I thought you were going to be the first one to get it when you reached for your calculator, and instead you reached for your calculator to divide by 100. Double disappointment. Redeem yourself, Nick. In your head, 6 minutes. How many seconds? Can you do it? Thank you. Okay, you're back. 360 seconds. What do you get? And give this to me to all of its decimals. I think it works out to 1 decimal place. Give it to me, I think, to 4 sig figs. Something in the hundreds, but I can't remember what more than that. Yeah. Sorry? How many steps did they take? That's the height. Well, one step is 0.22, right, 22 centimeters, 0.22 meters. And how many times did they do that step? 300. How much height did... I realize they're staying in one place, but had they not, that's the height they would have climbed. Is that okay? This is how the machines run the numbers. What'd you get? 161.7? Is that right, folks? That means this machine would say that every second you were burning 161.7 joules of energy. You're not, though, first of all. That's only the energy that you're burning stepping up and down. What does B want me to find, Nick? Okay, this is definitely power. Which power? Well, you're also burning energy as heat. You're sweating. Your body is giving off a lot of heat. What haven't I used yet? Efficiency. You know what? I think I'm going to use efficiency equals power out divided by power in. Or smaller number divided by bigger number. So the question here is, that 161.7 watts, is that going to go where the smaller number is, power out, or where the bigger number is, power in? In other words, on an exercise machine, whatever the computer thinks you're doing, which is what we did in part A, is that more or less than what you're actually doing, burning off heat and things like that? That's the computer has it as less. You're doing way more because your body's giving off heat. The software can't measure that. So that 161.7 is the smaller number. I want to find power in. Nick, where is the power in? On the... Yeah. Let's do the same trick. Let's multiply the power in to the top and bring the efficiency to the bottom. Let's rewrite this as power in equals power out divided by efficiency. It's going to be 161.7 divided by 18? No. What will I divide by? So yeah, we never do math with percents. Which is what? So I'll call it 898, close enough, watts. So your body is actually burning 898 joules per second. This is why I said to you, exercise machines are garbage in terms of telling you how much energy you burn. First of all, unless the exercise machine asks you to type in your mass, that's nonsense, because just to figure out the basic calculation, there is an M in the equation. If they don't ask you to enter your mass, two possibilities. There might be sensors that measure your mass. I doubt that, unless it's a really, really high-end exercise machine. Or they're taking an average mass, which is also, to me, nonsense, because what's the average mass of people who exercise regularly? I don't know. Would that be higher than normal because they're trying to lose weight? Or would that be lower than normal because they're already in good shape? Or would that be, I don't know. So first of all, it doesn't ask you for your mass, it's garbage. Secondly, even this, if they want you to actually calculate how much energy you burned, how much work you did, how much power you did, they would need to know your metabolic efficiency. It doesn't know that. So it's making an average guess. By the way, if someone is out of shape, would their body be more efficient or less efficient? So this number on the bottom would be smaller. It means that people who are out of shape are having to do way more work, generating way more power, which means, I'll take your question in a second, which means way more joules of energy per second. So it's really tough. It's kind of a vicious circle. People who are out of shape, it's more effort for them to get back to the point of being in shape next to somebody else. And so often they won't make that effort because they look and they see, some triathlete sitting on the treadmill going like blazes, and they think, oh, I'll try and do that, and they can't even come close to that, and they quit. So enjoy your young, in-shape bodies while you have them. It's all downhill from here, says Mr. Dueck, who turned 50 this summer, but there's some physics of exercise machines. You were going to ask a question.
Have you seen like the ones that have the sensors on the handles?
Are those heat sensors, or are those pulse? No, they're pulse sensors. They're measuring. They're taking your pulse. And so they're trying to also extrapolate from your heart rate to see, how much work you do. Or they're trying to make a guess as to whether you've got your heart rate in the zone. There's this imaginary, you should be running at X percentage of your maximum heart rate. That's when you're at your best. But again, they're taking average values and going best guess. Really, they're bells and whistles. Don't take them too seriously. That's all I'm saying. What's your homework? First of all, you can now do every question on the ultimate review. You can try number 2 and number 3. Number 7. Number 9. Number 9, B. So first of all, there's a ramp in number 9. You can do this with angles, but I'm telling you, you can also do number 9B cleverly with work and energy, because it didn't give you theta. You can calculate theta, because if you draw the triangle, you know the height, you know the ramp length. You could use shift sine or shift cos, and you can find angle theta, and then you can figure out what is the constant for. You can do it with just work and energy. 10 is good. 11 is good. This is the only question I'm going to give you where there is an angle, and that's just for you to practice so that you know, okay, I can handle it. And 14.